In section 1.5, we're going to talk about scientific notation. Again, I would be very surprised if this is something you haven't seen before, so this will be kind of a short one today, I think. Scientific notation is a common way that we write really, really big numbers and really, really little numbers. And it has everything to do with multiplying and dividing by powers of 10. So let's say I were to give you 8.56 and multiply it by 10. Notice all that did is it moved the decimal one place. We went from 8.56 to 85.6. What if I took 8.56 and multiplied by 10 squared? 10 squared is a fancy way of saying 100. It moves the decimal two places. Power 2 moves the decimal two places to the right. 8.56 times 10 cubed. You probably know the answer already. It moves the decimal three places to the right. So it's 1, 2, 3. We end up with 8,560. Now, what about multiplying by powers of 10 that are negative? What if I give you 8.56 times 10 raised to the negative 1? Well, think back for a minute to section section 1.4, part A. We know what negative exponents do. All this negative exponent does is really drop this 10 down to the bottom, and it becomes a division. So really, instead of multiplying by 10 here, I'm dividing by 10. Dividing by 10 moved the decimal 1 to the left. 8.56 times 10 raised to the negative 4. All right, now your calculator writes this in scientific notation. What this does, I don't like the answer the calculator gave me, but it's the right answer. It moves the decimal 4 places to the left. So let me do 8.56 times 10 raised to the negative 3 so we can see that better. So it takes this decimal, moves it 1, 2, 3 places left. All right, so this is the calculator's way of writing scientific notation. 8.56 times 10 to the negative 4 is what this E stands for. It's not 8.56 to the negative 4. That's a very different thing. 8.56 raised to the negative 4 is a very, very different number. Okay, let's go to the problems. Convert to ordinary notation. We have a positive exponent. Positive exponents move the decimal to the right. So this is going to move 7 places to the right. So there's 1 place. And then 6 more means we need 6 zeros. So that's a fancy way of writing 35 million. 8.26 times 10 to the negative 9. Negative exponents move the decimal left, gives you really, really tiny decimals. So we're going to move it 1 there, and then we've got to go 8 more. So that's 8 zeros, and then an 826. All right, now going the other way, convert to scientific notation. The first thing, when we write our number in scientific notation, this first number here has to be, I'll call that number A. It has to be between 1 and 10. And it can be the number 1, but it cannot be the number 10. So in other words, this number, 0.000045, we're going to put the decimal point between the 4 and the 5. And then it's times 10 to the negative. I know it's negative because this started out as a decimal. And I just count. How many places did I need to move? 1, 2, 3, 4, 5. So that's 4.5 times 10 to the negative 5. All right, this next number, we put the decimal between the 3 and the 7. 3.793 times 10 to the, and now we got to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. and it's positive. Positive because it's a big number. Big numbers have positive exponents, little decimals have negative exponents. Okay, now this is something you might also see. Convert the following to engineering notation. Engineering notation is very much like scientific notation, except these exponents always have to be a multiple of 3. 3, 6, 9, 12, so on and so forth. And the reason they like multiples of 3 are, think of like 10 to the third is 1,000. 10 to the 6th is 1,000,000. 10 to the 9th is 1,000,000,000. So it's easy to convert to thousands, millions, billions using multiples of 3. Okay, so how are we going to write these numbers so that the powers are multiples of 3? So we can't use a power of -5, but we could use a power of -6. So what would have to happen to use a power of -6? Well, if we're going to decrease the power here, that means we need to increase this one. So if we make this number smaller, -6 is smaller than -5, we need to make this number bigger. So this one would be 45 times 10 to the -6. So notice you're no longer restricted to the between 1 and 10 rule. Now you're restricted to between 1 and 100, because 10 squared would be 100. Actually, I guess you could go up to 1,000. 10 cubed would be 1,000. All right, so this one, we want it to be a multiple of 3, 3, 6, 9, 12, so we could use 12. So again, we're making this number smaller, which means we need to make this one bigger. So this would be 37.93 times 10 to the 12. All right, so the engineering notation, that one's a little weird for me. I don't use it. But then again, I'm not an engineer. So, all right. Perform the operations without a calculator by converting to scientific notation. Assume all values are exact. All right, so what they're telling me to do is put it in scientific notation first. So this would be 2.8 times 10 to the 4th. And then we're going to multiply that by 3 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so all we really have to do at this point is multiply 2.8 times 3. 2.8 times 3, 8 times 3 is 24, carry the 2. 3 times 2 is 6, plus 2 is 8, so that's 8.4. So this is 8.4 times 10 to the, and again we go back to our previous section, here we add the exponents. 4 plus 9 is 13. All right, this one, similar thing. 8 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, 9 divided by 2 times 10 to the 6th. And really, this is one of the big reasons for using scientific notation, is it makes multiplying and dividing pretty easy, especially back in the days when we didn't have calculators. 8 divided by 2 is 4. And then we subtract our exponents. Negative 9 minus 6 is negative 15. So that's 4 times 10 to the negative 15. All right, then it asks, how would the answers change if values were approximate? Well, if values were approximate, then for this one, I only have one significant digit. So I would have to just call this one 8 times 10 to the 13. This one, however, would not change, because I have one significant digit there, one significant digit there. I only gave one significant digit. So this one would change, this one would not. All right, use your calculator to evaluate. All right, so calculator. .62 times 10 raised to the 5th times 6.245 times 10 raised to the negative 6. I'm going to get that answer. And then I'm going to divide by, now be careful. When I divide, I need to do that multiply first. Remember, this big fraction bar is a set of parentheses. So I need to put that denominator in parentheses, and that's the most common mistake people make with these problems. So it said, use your calculator to evaluate, assume everything are approximate. So I've got 3 sig figs there, 4 and 3. So I can only give 3 sig figs. So I gotta call it 422, comma, I don't know if the comma goes there. 1, 2, 3, 4, 5. It does not go there. 1, 2, 3, 4, 5 zeros. I don't like the way that looks. I'm going to rewrite it. 422 with 5 zeros, which means 1, 2, 3, 4, 5, 5, 6. The commas go there. Nope, that's still wrong. Comma goes there. Sorry about that. That's ugly. Can't put the comma in the right spot. Your other option for doing this is to use the calculator's scientific notation, which is this EE button. You can't see it because it's too low. This EE button. So I'm going to redo this problem. I could do 3.62 E5. That means 6.32 times 10 to the 5th times 6.245 times 10 to the negative 6. And the advantage of this is I don't think I need the parentheses. I think the calculator knows to put that bottom all together. And we'll find out. We'll see if it gives us the right answer. It did. It gave us the same answer as before. So that is an advantage to using the E notation on the calculator, is then you don't have to worry about the parentheses. The calculator knows to do this multiplication. It knows these go together before doing the division. All right, last problem. A computer can do an addition in 7.5 times 10 to the negative 15 seconds. How long does it take to do that many additions? Well, you just multiply 7.5 times 10 to the negative 15. That's how long it takes it to do 1. And then if I wanted to do 2, of course, I would double that. If I wanted to do 3, I would triple it. So if I want to do that many, I multiply by that many. So 7.5 times 10 raised to the negative 15 times 5.6 times 10 to the 7th. It's going to take it 4.2 times 10 to the negative 7 seconds to do, that's what, 56 million addition problems? So we can do 56 million additions in less than a millionth of a second. Computers are pretty amazing. All right, relatively short section, like I said. Should be a pretty straightforward one for you, I think.